Hey guys, today we're going to be going over a lesson of the history of the atomic theory. So essentially we're going to be looking at all the different scientists that contributed to our understanding of the atom and some scientists that were way off. Okay, so like I said, this is all about the different theories of the atom. We're going to essentially just cover, like I said, a bunch of different people. Um, from this, you do need to know what each person kind of contributed to this understanding. You do also need to know all of the different parts of the atom. You have to be really familiar with the kind of last one that we're going to be talking about. Okay, so first of all, what a scientific theory is. It is an educated guess based on scientific reasoning and interpretation of evidence. And as we gather more information, theories can change and evolve. That is why we have this whole history of atomic theory, because as scientists had access to more tools, they were able to do more experiments, and that allowed them to gather more evidence, which then changed and evolved the theories that we had. So we started way back with Democritus in 400 BCE, which stands for before current era. He was a Greek philosopher who said that all matter can be divided into smaller and smarter particles until you're left with an invisible particle that cannot be divided. And he named this particle the atom. He also said that atoms are different sizes, that they're in constant motion, and they're separated by the void, which is just his term for empty space. Even though Democritus was a philosopher long before he had access to any type of technology to see these invisible particles, he was spot on. Nothing that he said is wrong. He might not have the full idea of what an atom is, but he did know that atoms are different sizes, which are true, that they're constantly moving, which is true, that they're separated by empty space, which is true, and that they can't be divided. So all of this is spot on. Also, look at that guy. I mean, how can you not like him? Then we move on to Aristotle. He was also a Greek philosopher. He was in 450 BCE, and he completely rejected the idea of the atom. He claimed instead that all matter is made up of 4 basic elements, and he wasn't talking about elements like what we see on the periodic table of elements. No, he was talking about things that aren't elements at all: fire, water, air, and earth. Now, I cannot stand Aristotle. He honestly, he was a great Greek philosopher when it came to things like ethics and politics, but man, he should have stayed in his lane and not gotten into science, because his science didn't involve any actual science at all. He created hypotheses, which is what this was, but then he didn't experiment on them or actually gather any evidence. And what makes me so mad is that people trusted him because he was such a good philosopher in areas like ethics and stuff like that. So when he came out and said there are only these 4 elements, people believed him, and this theory was accepted for 2,000 years. It could not have been more wrong. Anyway, moving on. Finally, in the early 1800s, we get John Dalton proposing the invisible particle theory, which essentially comprised of 4 main points: that all matter is made up of tiny invisible particles called atoms, that all atoms of an element are identical and atoms of different elements are different, and that atoms are never created or destroyed, just rearranged in chemical reactions to form new substances. Now, most of this information is actually totally in line with Democritus's idea of what an atom is. And again, this is all still totally right. We don't disagree with any of this now. We've just built on this and added more information, but all of this information is true. Then we get to the plum pudding model, which is based on J.J. Thomson's discovery of small negatively charged particles called electrons. Now, he didn't name them electrons, he just referred to them as negatively charged particles, but that is beside the point. He discovered electrons. It was called the plum pudding model because he thought that the electrons were like inside the main body of the atom, and then that main body was positively charged to balance out the negatively charged electrons. So this is like what a picture of that would look like if an atom was actually plum pudding. This is a diagram of kind of what he envisioned, so that again, that kind of main body is positive, and then you have all these negative electrons floating around inside. Because most people don't really know what plum pudding is nowadays, this is sometimes referred to as like the chocolate chip cookie model, where essentially the cookie part is the positive area and the chocolate chips are the negative area. It is important to note that while this discovery of electrons was very important, most of the rest of this wasn't really accurate. Electrons are not inside the main body of the atom, and it's not all just like positive like that either. But anyway, next came something called the gold foil experiment, which was done by Rutherford, who's another scientist. Rutherford predicted that positive and negative charges were evenly distributed in the atom. If that were true, positive particles that were shot at a thin piece of gold foil would be deflected at small angles, or passed, as they passed through the gold foil, would be slowed down. So what he did, I mean, you can kind of see a diagram of this at the bottom. He took an incredibly thin piece of gold foil, like the kind that would be put on top of like food if you were at somewhere super fancy. Super thin piece of gold foil. He took a kind of like a particle gun, a basic particle gun, and he shot positive particles at the gold foil. And then he used this fluorescent screen that wraps around the outside to just detect where those particles were hitting. It would light up wherever the particles were hitting. And so what he found was that most particles just went straight through the gold foil, didn't slow down, like it was like they were just passing through air, just no effect when they went through the gold foil. And a couple deflected off at really wide angles, which is totally not what he was expecting. It was the opposite of what he was expecting. And so what he learned from that was that there is, in the atom, most of a substance is actually empty space, which goes back to what Democritus said about the void. So yeah, he learned that atoms are actually not as solid as we thought they were with that whole like billiard ball model or plum pudding model. The atom is actually a lot of empty space, and that in the middle of that empty space is a highly concentrated, dense, but small mass of positive charge. So all of what we thought was an atom, the atom is still that big, but all of that mass that we thought was there, all that stuff that we thought was there, is actually condensed into just a tiny little region in the middle of the atom, and then most of that atom is empty space. So based on that, Rutherford came up with what he called the nucleus of the atom, the nucleus being the term for that tiny, dense little area of matter in the middle of the atom. And he also discovered that it was positively charged because of the way that it would deflect the few positive atoms that actually hit it. So yeah, so the nucleus is very small, which is true, that it's where almost all of the mass is in the atom, because again, most of it's empty space. And that the negative electrons aren't in that nucleus because the nucleus is positive. So the electrons, he said, are actually like floating around in a cloud in the empty space that is surrounding the nucleus. And he was right about the nucleus. That's spot on. And the fact that most of an atom is empty space. So in doing these experiments, not only did Rutherford discover the nucleus, he also discovered the proton, which is the positively charged particle inside the nucleus. He then also measured the mass of these different atoms and noticed that the mass of the protons did not account for all of the mass of the atom. So he said there must be a third particle in the atom that weighs about the same as a proton in order to make up for the missing mass that he couldn't account for, but that it must be neutral because the positive protons and the negative electrons were already balancing out. So that third particle must be neutral, but he didn't discover what it is or where it was. That came from Chadwick, which was actually a student of Rutherford's. He discovered the neutral neutron, which is what we now call it, inside of the nucleus. So based on the discoveries of Rutherford and Chadwick, they proposed the planetary model, which said that an atom is empty space with a small, dense nucleus in the middle. That nucleus contains the protons, which are positive, the neutrons, which are neutral, and that the mass of the neutrons and the mass of the protons are about equal to one another. If you add those together, it accounts for the mass of the atom as a whole. They also said that the electrons are negative and rapidly circle the nucleus in that kind of empty space area. So this is kind of what this would look like. They're all just kind of circling around in that cloud. It is kind of important, not necessarily to memorize this in a chart form, but you do need to know where we find protons, neutrons, electrons, what their charges, and what their relative masses are. Protons are positive, neutrons are neutral, electrons are negative. Both protons and neutrons are located in the nucleus. Electrons orbit the nucleus. And protons and neutrons both have a mass of 1. Electrons have a mass of about 0. We consider it 0. Okay, so I mean, everything that they said about the nucleus was right on. The electrons, not so much, but we'll get to that with Bohr. So Bohr studied the light produced by hydrogen atoms when they were excited by either heat or electricity, which is a type of energy. So what he would do is he would provide energy to these hydrogen atoms in the form of either heat or electricity, and then see what happens. And what he would see is that the atoms would release light or fluoresce. And the reason that that happened, what he determined, was that the electron, which is this black dot right here, this is the nucleus in the middle, this electron was being excited, or it was moving to a higher energy level when it absorbed energy. And then as that energy stopped being absorbed, the electron wouldn't be able to maintain its excited state. It wouldn't have enough energy to stay in the higher energy orbital. And so it would fall back down to the lower energy orbital that it had started in. And when it fell back down, it would actually release light energy. So from that, Bohr came up with a proposal that electrons orbit the nucleus not just kind of at random, but in specific energy levels. So each electron has a specific amount of energy. The further the electron is from the nucleus, the more energy it has. And so what Bohr said, or what he came up with, is something called orbits or orbitals that these electrons exist in. The first orbital is the one that's closest to the nucleus, and then second and third and fourth, and so on. He said that electrons have to fill up the lowest energy orbitals first, or the ones that are closest to the nucleus first, and then when that one's full, they'll start filling up the next one and the next one and the next one. He said the electrons cannot exist between the orbitals, they have to be in them, but they can jump from one to another, like what he saw when he excited the electrons. They can also fall back down. Each orbital can only hold a limited number of electrons. The first can only hold 2, the second and third can both hold 8. So based on all of that, the final theory that Bohr proposed was called the Bohr-Rutherford model, based on both Bohr's information about the electron orbitals and Rutherford's and Chadwick, his students, information about what the nucleus looked like. This model works perfectly for the first 20 elements of the periodic table. It completely falls apart for the remaining like 100 elements. However, this is the model that we use in grade 10 and 11, and I think here in grade 12 as well. You might finally learn about the quantum mechanical model in grade 12. But anyway, for this year, you just have to know about the Bohr-Rutherford model. There is also the quantum mechanical model, where we get back to electron clouds instead of the traditional orbitals, but the clouds don't just go the whole way around. They're in like specific shapes, and there's like the D shape and the S shape and the P shape. And it's just based on the probability of where electrons will be at any given time. That's what the shape of the cloud is. Anyway, you don't actually have to worry about that for now. Just know that the Bohr-Rutherford model, which we're going to be using for the next 2 years, isn't really accurate, but we're going to use it because it does work really well to describe the properties of the first 20 elements. And most of the elements, like 2/3 of the elements that we're going to be using this year, are those first 20. So yeah, that's kind of it. We are going to be drawing Bohr-Rutherford diagrams later in this unit. But for now, that's kind of all you need to know about this.